Static and dynamic analysis of radial engine master rod using ANSYS. 1. Introduction. Radial engine is an interconnecting motor design with the cylinders rising from a central crankshaft as well as from a wheel in the up and down direction. Since the use of turbine engines, radial engines were typically used for a number of aircraft. In a radial motor, the cylinders are connected with a master rod. One piston is connected to a master rod in which the crankshaft can be mounted directly. The other pistons are fixed to the rings around the end of the master chain. The reciprocal load described on the piston after the spread and even compressed by all rotations, the master stroke undergoes tremendous stress. The load raises to the third power and the engine speed decreases. The failure of a connecting rod, that is usually referred to as a rod throw, is one of the most common reasons for the catastrophic failure of the engine in aeroplanes, which frequently throws the damaged rod across a piston side and even makes the motor irreparably tired of the rod. Lubrication of failure of a bearing due to a body fatigue have been published according to stress deformation. All the integrated factors were based to determine the effects and the variance of the static and dynamic stresses of the master rod used in the radial engine by combination impact research on static and dynamic analysis. When the modal analysis decides how the variance in the configuration from the analytics category is performable, the overall speeds, stresses, deviations from various loads, adjust the rotary speed and the speed imported for the master roll are calculated for aluminum alloy and structural steel material. 2. Literature survey. R.Ravi, et.al. One paper offers with the study of exploring the load and price reduction, but we've got taken the forged steel as the comparison for the material which is better and how to deal with substances in connecting rod. The paper has undergone detailed evaluation of joining pole through dynamic examination of linking bar considered. In the analysis of first part, it offers with the observe of static load analysis and materials which is chosen after which taken into account and by using maintaining the production as taken into account. Then in this paper it deals with layout of connecting rod through CATIA. Then the connecting rod is imported to ANSYS workbench and analysis performed on this paper. Results are acquired by comparing experimental results. Gurumachaudhry et.al. 2 radial motor displays have long been used in aviation, where the radial motor uses very less energy compared to an inadequate output in contrast with other motors. Then utter engine output was transformed in the present turbine engines. They substitute the motor and its output with this paper. A 5-cylinder Moki S is tested and checked through the FIA project. The engine's construction is carried out using CATIA V5 and ANSYS obtains a safety factor. Srikanth Kumar et.al. 3 This illustrates the function and use of the radial engine with respect to the master rod, while the piston is mounted with a master rod with an instant crankshaft connection. The remaining pistons are connected to the bottom of the master round by their connecting rods. 4-stroke radials have an unusual number of cylinder rows per row, so that the order of the fire piston can be preserved in a consistent way, so as to promote activity as the different documents. The layout is built in Pro-E, the study in ANSYS 13.0 is done. 3. Methodology. The sequence of methodology is listed below. Problem formulation and identification through literature survey from various ASME journal, Wikipedia and websites collected towards the present research topic. Understanding the working principle of the master rodist in radial engine and reasons for its failure. Modeling of master rod of different geometry in CATIA V5 R20. Static structural analysis in ANSYS 14.5 workbench carried out to determine structural strength of the master rod. Fatigue analysis of master rod of radial engine in ANSYS 14.5 under different boundary conditions carried out to determine the failure life of master rod. Selection of materials for the master rod. Applying the material property for the master rod. Comparing the materials and showing that which material is best for the master rod. Comparisons and validations of the results and improve the fatigue life. 4. Design of the master rod. Span of the connecting rod. Radius of the hole and diameters of crank end and piston end. Diameter 4 to 5 dimensions should be noted. Length of the rod should be noted and length between crank end and piston end should be noted. Finally, All the steps should be followed. All dimensions are importing in CATIA V5 R20. Design should be made according to the dimensions oft assumption made in the given engine. 5. Calculation of master rod. Maximum stress of 131.28 MPa which is shown in red color region and minimum stress of 0.04 MPa which is shown in blue color region. Yield strength of steel material is 250 MPa, working stress is 131.28 MPa nearest or time fewer than the harvest asset of the substantial hence rotational velocity of 6000 rpm to radial engine connecting rod is applied by considering the factor of safety within the range of 1.5 to 2. Aluminum alloy. Fig. 6, deformation in the rod for Al alloy. The total deformation for aluminum alloy, maximum deformation of 0.33 mm and minimum deformation of 0 mm. Maximum stress of 157.71 MPa shown in red color region and minimum stress of 0.04 MPa shown in blue color region. Yield strength of steel material is 380 MPa, working stress is 157.71 MPa is smaller than the harvest forte of the material hence we can give rotational velocity of 11,000 rpm to radial engine connecting rod, considering the factor of safety within the range of 2.4 to 2.8. Structural steel. The variation of fatigue life for rotational velocity for Al and steel represented in graph 5. It is observed that fatigue life of Al is more when compared to steel material. The variation of factor of safety for rotational velocity for Al and steel represented in graph 6. It is observed that factor of safety for Al is more when compared to steel material. By this positive result, it is observed that Al material have higher fatigue strength and structural strength than. 7. Conclusions. The static analysis maximum equivalent stress distribution in radial engine connecting rod is 131.28 MPa. The maximum stress occurred at crank end and yield strength of steel material is 250 MPa, working stress is 131.28 MPa, which is much less than the yield strength of the material hence rotational velocity of 6000 rpm to radial engine connecting rod is applied by considering the factor of safety within the range of 1.5 to 2, once increased in rotational velocity above 6000 rpm for steel, connecting rod will leads to fail, hence maximum rotational velocity should be within 6000 rpm for steel material. The static analysis the equivalent stress distribution in radial engine connecting rod is 157.71 MPa. The maximum stress occurred at crank end and hence it need to take care about the thickness of the crank end. Yield strength of aluminum alloy is 280 MPa, working stress is 157.71 MPa is lesser than the yield strength of the material hence providing rotational velocity of 11,000 rpm to radial engine connecting rod, considering the factor of safety within the range of 2.4 to 2.8. Once it increased rotational velocity above 11,000 rpm for aluminum alloy, connecting rod will leads to fail, hence. Maximum rotational velocity should be within 11,000 rpm for aluminum material. The total deformation distribution in radial engine connecting rod is 0.09 mm. Minimum deformation is 0 mm. Because at the fixed end geometry does not allow to deform similarly for aluminum maximum deformation of 0.33 mm and minimum deformation of 0 mm fatigue life 1.19 x 105 cycles was observed in the geometry, it clearly shown in red color region at crank end and maximum fatigue life 1 x 106 and similarly for aluminium fatigue life 2.94 x 105 cycles and maximum fatigue life 1 x 108. Aluminium alloy has 59.52% more fatigue life and strength than structural steel. Acknowledgements. I would like to express my profound gratitude to Dr. Mohammed Imran, Assistant Professor in Mechanical Engineering Department, Gauziya College of Engineering, Raman, for his guidance and useful suggestions, which helped in completing the project work in time. I express my sincere thanks to beloved Principal Dr. A.R. Anwar Khan, Gauziya College of Engineering, Raman, for providing me an opportunity to fulfill my desire of reaching my goal and thus helping me to make a bright future. I express my sincere thanks Sagar Sr., Department of Mechanical Engineering, Amrita Institute of Engineering and Management Sciences, Polytechnic, Bidadi, Raman Agram, for providing me an opportunity to fulfill my desire of reaching my goal and thus helping me to make a bright future. I would also thank all the Gauzia College of Engineering teaching and non-teaching staff of Department of Mechanical Engineering for their kind support during the course of work. The support provided by the department library is gratefully acknowledged.